guys, I'm going to try to do this from home and see how this works out. This is going to be chapter 8. We're actually going to go through 8.1, 8.2, and 8.3. If you watched the other videos, I thought we'd actually go back to school, so I kind of went through them not thinking, but now that I think that we're not going to, I'm going to go ahead and go real slow and talk to you about them and things like this. Even though you guys can pause this and whatever, there's going to be two papers I'm going to use. This one that says page 601 at the very end, just to walk you through a few examples. And then the most important page is this testing series for convergence or divergence. Okay, so those are the two I'm going to refer to. I'll try to get as close to this. I have it propped up, so I don't know exactly how this is going. So, chapter 8. What 8.1 begins with is the difference between a sequence and a series. A sequence is just going to be a group of terms, so it's just a bunch of numbers. A series is going to be the sum of all those terms. So for instance, if I give you the function 1 over x squared, this is the notation they'll use. They'll use braces and they'll say a to the n, and they'll say, hey, a sub 1 means you go over and you put 1 in for the variable. So a sub 1 is 1 over 1. A sub 2 means you'd put 2 in, so you'd get 1 over 4. And a sub 3, you'd put 3 and you get 1 over 9, and then continue to do that. So a sequence are just the numbers 1, 1/4, 1/9, and you can keep going on forever. So the sequence are just these numbers. They're called elements, just like if we're in a matrix. But a series is what we're going to talk about. A series will look like this. They'll have the Greek letter sigma. This is the capital sigma. In mathematics, it means summation. So if I see the summation, this tells me that my variable is going to go from 1 to infinity. Yes, that's infinity. Don't make fun. And I just made the function 1 over n squared. So what a series does is it takes all these elements and it adds them together. So you put 1 in here. So 1 over 1 is 1. You'd put 2 in, you'd get 1 over 4. You'd put 3 in, you'd get 1 over 9, and so on and so forth. So the mathematical series is the sum of all these things. So what we're going to do in chapter 8 is I'm going to give you a series, and you're going to have to tell me if it diverges or converges. And then you're going to have to tell me every once in a while, if it converges, we can actually find out what all those numbers will add up to, essentially. So, in chapter 8, we're going to decide if it converges or diverges. What converges mean are that these things are actually going to add up to be a specific number. That means that this fraction is going to get so minutely small that when you add it, it's really not like adding it anything. And so it's actually going to sum up to be a particular number. It's going to get closer and closer to some particular number. Diverge means that it's just going to keep getting bigger and bigger and bigger and bigger. All right? So when I give you a series, you're going to say it either converges or you're going to say it diverges. There's going to be two instances where I'm going to say, hey, find the sum. These are going to be the two instances where you find the sum. The first is going to be called geometric, and the second is called telescoping, which I'll go over both those today. So real quickly, we have sequences, which is just my terms themselves, just a group of them. Each one's called an element. The series is going to be the sum of them, and that's what we're going to look at. And we're just going to ask ourselves, do our series converge or diverge? All right. So if you look at this paper, the one that has all these crazy tests on them, what we're going to end up doing is we're going to talk about half of them right now, and then I'll give you some homework and you can try to do the other ones. Now, the idea is I'm going to give you a series. I'm going to ask if it's going to converge or diverge. So the first one that I actually want to go over is on this. It's called the kth term test. Now, some books will call this the nth term, just meaning as we keep going out and out, what's going to happen. If you look at this, the kth term test, it says that if the limit as k approaches infinity, and in this case, they say a to the k equals 0, does not equal 0. So in essence, what we're going to do is we're just going to look at our variable approaches infinity. Here's the idea of it. If it does not approach 0, it's either number 1, getting bigger and bigger and bigger, which let me give you a quick example like that. So if I said that I'm going from 1 to infinity of, let's just say, 2 to the n power. When I keep plugging in, I'm going to get 2, I'm going to get 4, I'm going to get 8, I'm going to get 16. If you keep adding this up, it keeps bigger and bigger and bigger, right? This thing is never going to converge. So that means this is going to diverge. And instead of you just telling me, you need to give me the exact reason why it's going to diverge. And you would say that the limit as n approaches infinity of 2 to the n equals infinity. It is not equal to 0, so it diverges by the kth term test. Now, if you said the nth term test, that would be fine too. Okay, so the idea with the kth term test is, and I labeled this one first because this is the first one that I use. If I look at the function and I know that it's getting bigger and bigger and bigger, I don't need to do any other tests. I can immediately say it's going to diverge. Because if we have a series and we're adding numbers and that number keeps getting bigger and bigger, it's always going to keep getting bigger and bigger. So the kth term test says, hey, if my limit of that function is not 0, or if that term is not 0, then I can immediately say that it's going to keep getting bigger and bigger. Even if my limit happens to be a half, like in this case. Like if I just, said, okay, tell me if this series converges or diverges. And I just said something like 2n plus 1 over 4n plus 3. Something like this. The idea with this is, hey, whenever we found limits as x approaches infinity, we always compared the degrees, right? So what is the limit as n approaches infinity of this function? Well, remember the rule that if the degrees are the same, it's the ratio of the lead coefficients, which is 2 over 4, which ends up being 1/2. So this limit's approaching 1/2. That means that as n keeps getting bigger and bigger, this thing's getting closer and closer to a half. But when you keep adding a half and a half and a half and a half, you're continually getting bigger. Therefore, we can say that this diverges by the kth term test. So the first test I wanted to go over is the kth term test, and it's just written right here. It says kth term test. If the limit is not 0, the series diverges. That's the first thing I always look for when I'm asking if a series converges or diverges. Because if it keeps getting bigger and bigger, or if I see that it's a rational expression and the limit's going to be like 1/2 or any constant, then I immediately know it's going to diverge by the kth term test. All right, so that's the first test I wanted to go over today. Now, the second test I want to go over is what's going to be called the geometric series test. Now, if you read this front part, you're going to see that if you can set it up with the summation as k goes from 0 to infinity of a times r to the k, if we can set it up like this, we can always use the geometric series test. Okay, so my variable is in the exponent. That's going to be the key here. Some of you may say, well, you always go from 1. Almost always we go for 1. 1 to whatever. With geometric, they usually go from 0. But if they go to 1, if they start at 1 and it's geometric, we'll have to worry about compensating for that later on in the homework, and we'll talk about that later. But the main thing is just this test. If it's set up to where I have a variable here, then I just apply this. And if you just read it here, this is like your cheat sheet. It says that if your base is less than 1, it's going to converge. Not only is it going to converge, but it's going to converge to a over 1 minus r. Meaning we can tell what all those numbers are going to keep getting closer and closer to. It's going to converge to a particular constant. Now, if my base is bigger than 1, it diverges. I'm going to explain what that is in a second because we can kind of go hand in hand with things. So, I just want to give you some quick examples. So the first one would be as n goes from 0 to infinity of 5 times 3/2 to the n power. So if it's set up like this, if I have something to the n power, I can immediately say, hey, I can apply the geometric series test. So to do it, I look at this r. Now in this case, r, the absolute value of it is bigger than 1, right? If you look at this, this means that I can automatically say that it diverges by the geometric series test. Now, why is that the case? This goes hand in hand with what we just went over. if this base is bigger than 1, it's really a growth model. If this base is bigger than 1, as then it gets bigger, this thing's going to get bigger and bigger and bigger and bigger. It's never going to, you're never going to be able to converge it because it just keeps growing and growing and growing. So those two things kind of tie in together. So you could have said for this one, hey, the limit is not going to be 0, it's going to be infinity. So you could say this diverges by the k-term test also. However, if it's set up in the geometric series like this, we kind of like to use it. So if your base is bigger than 1, you automatically say it diverges by the geometric series. Now, an example like this, if I have 3 to the 1/2 to the n power. So that's a 2. 3 to the 1/2 n. So now I want to look at this series. If it's ever set up to be something to a power, if I can make it look like this, it's the geometric series. So to see if it diverges or converges, I look at the base. My base is less than 1. So that means that this thing is going to converge by the geo series test. But more importantly, this is one of the tests where we can find out what it's going to actually add up to be. And if you look, the sum is always going to be a over 1 minus r. A is going to be the number out front, which in this case is 3. If there's no number out here, we just assume it to be 1. 1 minus r, so in this case, it's going to be 1 minus 1/2. Hopefully all of you know that 1 minus 1/2 is 1/2. 3 divided by 1/2 is going to be 6. So this converges, but not only does it converge, we can say that if we keep adding these numbers up, it's going to keep getting closer and closer and closer to 6. All right. Last one I want to give you a geometric series is sometimes it's a geometric series, but it's not always set up like that. So a good example of this is going to be like 6 over 3 to the n. So if you see something to the n power and it's only on bottom, you need to recognize that, you know what, I can make this look like a geometric series. You take your 6 out front, and then if your n is on bottom, you can write your base to be 1/3 to the n power. Those two are the exact same thing. And now I can say, hey, it's a geometric series. That means that my base is less than 1, therefore this thing is going to converge. So it's going to converge by the geo series. And not only that, I can find out what it converges to. You put a over 1 minus whatever your base is, so 6 over 1 minus 1/3, which would be 6 over 2/3, which would end up being 9, I think. But you can do that in a calculator, no big deal. So that's the geometric series test. If you have any questions on that, feel free to email me or you can text me and whatever. All right, so let's keep moving on. Just a few more and then we'll be done here. All right, the next is what's going to be called the P series. Now, a particular case of the P series is going to be called the harmonic series, which I'll go over that kind as we go. So if you look at this little thing, it's the sum of k to the p over 1, all right? So it's k goes from 1 to infinity, and in this case, it's 1 over k to the p. Now, this differs from the geometric series, because my geometric series, my variable's in the exponent. Here, my variable is my base, okay? So that's how you really tell the difference between the two. P is my power for power. And then the P series has this little test that says, you know what, if it's set up like this, to where it's k to the p on the bottom, if p is greater than 1, it's going to converge. So if p is bigger than 1, we know it's going to converge by the P series test. If p is less than or equal to 1, we're going to say it diverges. So this test we're going to use if you have a number or your variable to a power and it's on the bottom. Okay? So, let's get some examples. So for the P series, let's look at this one. The example as k goes from 1 to infinity of 1 over k squared. I actually gave you this one as like one of the series and sequences examples. So the question is, when I give you this series, I just want to find out, does it converge or diverge? If it's geometric or telescoping, which I'll go over later, I may want to find out what it converges to. But in this case, I just want to know if it converges or diverges. So if you ever have your variable to a power in the denominator, what you can do is you can look to the p-series. Since p is bigger than 1, we can immediately say that this converges by the p-series test. Right? That's as easy as it is. So let's look at another one. So we're going to go, k goes from 1 to infinity of, let's just do 1 over the square root of n. Okay, if I want to do 1 over the square root of n, the question is, does this series converge or diverge? If you ever have a variable, sorry, that should have been a k, my bad, or this should have been an n. As long as these match up, they will. Some books use k's, most use n's. So, since I have a variable to a power, I can use the p-series test. Just remember, the square root is the what power? Prater? Good, 1/2 power. Now, 1/2 is less than or equal to 1. So, if my power is less than or equal to 1, the answer to this question is that this diverges by the p-series test. Okay? So, let's look at just a couple more quick ones, and then you can tell me if it converges or diverges. Okay? So, let's look at this one. Let's just do 1 over k to the 5/2. 1 over k to the 5/2. Does this series converge or diverge? First thing is, what test do I use? If you ever have your variable to a power on bottom, you want to use the p-series. If this variable is greater than 1, you can immediately say, yep, this thing converges. So this converges, and you need to put by p-series. If you just put converges or diverges, you'll get 0 credit when I give you your assessment on this. I need to know why it either converges or diverges. So last one, 1 over n, since I changed this to an n. Okay, well, what's my power here? It's 1. It's less than or equal to 1, so this thing is going to diverge. This particular series is called the harmonic series. 1 over n is called the harmonic series. And if you look to the 4th test going down, it says the harmonic series, if it's 1 over k or 1 over n or whatever, it diverges. Okay, so that's just one test in itself. But I would just use p-series. It's just an actual example of a p-series when p is equal to 1. So that's why I use that. The alternating one, if you look at that, we'll actually discuss this when we go down to the alternating series test. So I'll skip over that one. So we went over geometric, p-series, k-term, and alternating. The limit of partial sums, we're not going to do that. If we had ample time, I would. But for this test, you can actually use almost, you can use other tests. Like I said, there's plenty of other tests. So sometimes when I give you one, there's not going to be just one answer. You could use numerous ones. In this case, if I give you one that you can use the limit of partial sums, you're going to be able to use something else. All right? If we have time, if we happen to come back to school, I'll definitely cover that. So last one I'm going to use is the integral test. So what is the integral test? This takes us back to 7.8, which I know some of you struggled with this anyway. Hopefully when I get your homework next time you guys drive by, we'll see how that goes. Oh, we are going to do the telescoping too, sorry. Integral test. How do you know when to use the integral test? Well, I eliminate the others. I eliminate the kth term, I eliminate the p-series, I eliminate the geometric. The integral test, if you see something that you know you can integrate, that's when you know that you can use the integral test. Now, there's a couple stipulations to this. The first thing is it must be continuous. And then the second thing is going to be that it must be decreasing. Okay, meaning that it keeps getting smaller and smaller. Once again, if you see something that keeps growing forever and ever, we immediately use the k-term test and say, hey, it's always going to diverge because the limit's not 0. So the limit must be 0 for this. That'll kind of say, hey, it's going to, get smaller and smaller and smaller. So this is what the integral test is. This is one of the harder ones. It says that if I'm going from 1 to infinity, okay, and then I have some example. I'm going to go ahead and I'm going to use one so you can kind of see what I'm talking about. Here is 1. Okay, I can't use my p-series, I can't use my geometric, I can't use the k-term because the integral of, or the limit of this is actually 0. That doesn't mean that it's going to be the opposite. Okay, k-term test only tells you that it diverges. It doesn't say, hey, if the limit is 0, that means it converges. That doesn't work. The converse doesn't. So when I get a problem like this, when I see n over n squared plus 1, I know the limit's 0, so I can't use the k-term test to say it diverges. So I look at this and I immediately need to say, can I take the integral? Well, if the derivative of the bottom is in the top, I can take the integral. That's going to alert me that I can use this integral test. Now, how do you do the integral test? Well, the thing is we do just like we did in chapter 7.6. We're going to take the limit as b approaches infinity of the integral of 1 to b of this function. So this recaps kind of what we did in 7.6. If I want to find a limit as from going from 1 to infinity, well, it's an improper integral, so what I have to do is change it to a limit. So in this case, what do? Well, you take the integral of this. Well, the derivative of the bottom is in the top. Remember, by u substitution, it should be a 2n, so this is going to be 1/2 ln of the bottom, right? Okay, then what do? Well, then you have to integrate it from 1 to b. So when I plug b in, I get 1/2 ln of b squared plus 1. And then I get minus 1/2 ln of 2. So what I do is I look at the limit as b approaches infinity to this. Okay? And then when you look at this, the integral test, it says that if this converges, it converges. If it diverges, then the series diverges. And it also says that if it does converge, it doesn't necessarily converge to that number like we say it does with the geo, and I'll go over the telescoping next. So what happens when I plug in infinity? Well, ln of infinity, if you remember ln graph, it looks like this. So this thing keeps getting bigger and bigger and bigger. So when I plug in infinity, I get infinity. That means that this limit is infinity. That means that this diverges. So if my limit diverges, that means my series diverges by the integral test. Okay? So this is going to be a harder one. If you can find another way, great, but sometimes you can't. But the thing is, make sure you can recognize, hey, can I take the integral of this? Because if I can, just say the limit as b approaches infinity of 1 to b of that thing, integrate it, put b in there, put 1 in there, and subtract it. And then you plug infinity in and see what you get. Let's do one more just because I know some people like Josie and Hannah and Grace are going to be like, hey, will you give me another example? Mariah's like, I don't need one, but that's okay. We're going to keep going. Joe, TJ, make sure you keep paying attention here. So the next one I want to go over is 1 over n squared plus 1. Does this converge or diverge? Once again, if I have a rational expression, I always say to myself, can I apply the k-term test? Well, the limit is 0, so I can't. If the limit was something other than 0, I would say that it diverges automatically. Well, I can't use the p-series because I have this plus 1. And then I can't use the geometric because it's the power is not my variable. So that, I look at this, I'm like, what is that? Well, if I flip these two around, I immediately say, I can integrate that. That's going to be the arctangent. So when I do this, I know I need to change this to be the limit as b approaches infinity from 1 to b of 1 over, and I'm going to write it like this so we have it as a squared plus u squared. Then if you remember, how do you go ahead and integrate that? Well, you get the arctangent of n over 1 actually, and 1 over 1 out front. And so what I want to do is I'm going to integrate this from 1 to b. So I want to find the arctangent of b minus the arctangent of 1. And then I'm looking at the limit as b approaches infinity of this. So you plug in infinity and you get the arctangent of infinity minus the arctangent of 1. If you remember, before we left, I told you one thing you needed to write in your notes is that arctangent of infinity ends up being pi over 2. just as a quick refresher why, if we look at, remember arctangent is saying, hey, the tangent of what angle is going to give me infinity? If we look at our first vertical asymptote of 5/2, this little piece of the tangent graph, as tangent is getting closer and closer to infinity, what angle am I getting closer and closer to? Pi/2. So that's why the arctangent of infinity is pi/2. Now, what's the arctangent of 1? Well, the tangent of what angle is 1? Well, that's your 45, 45, 90 triangle. And in radians, it's pi/4. So if you subtract this, you end up with pi/4. This converges. Now, this test doesn't say it converges to this number. But if this converges, we can say that the series converges by the integral test. One more. Okay, this one is not on there, so you need to really make sure you take notes on this. The last one is what's called the telescoping series. There may be other ways to figure this out, but this is one of my favorites. What the telescoping series is it's going to be a series that looks like this. How can you tell when you want to use this? If you can make this be a difference of two fractions, and it's kind of like our integration, which is one of the last problems I gave you on your last assessment. A couple of you I talked to in your cars and said, oh, I forgot how to do this one. If you have something you can factor on bottom, which I'll give you an example of that, but then you can break it apart to be a over one factor minus b over the other. If you can take a quadratic and break it into two linear ones, then you were able to integrate it. Well, in this case, it's very similar. So if I said 1 over n, and then 1 over n plus 1, and then this is a minus here. If you can break it up into two linear factors like this, and I'll show you how to do it in 1 second. But here's an example. I could just give you this series, and I say to you, hey, does it converge or diverge? The first telltale sign is this minus sign with two factors. I haven't given you anything with more than one term yet. So that lets you know, hey, this is going to be a telescoping series problem. How do you do a telescoping series problem? Well, what you're going to do is you're actually going to write out the first so many terms, and then you're going to see a pattern, and you're going to see that things are going to cancel out. So when I plug in 1, I get 1 minus 1/2. Plus, now n goes to 2. So I plug 2 in, I get 1/2 minus 1/3. Plus, now I plug 3 in, I get 1/3 minus 1/4. And then we keep going. If I plug 4 in, I would get 1/4 minus 1/5. Sorry about that. 1/4 minus 1/5. And we can keep going on and on. But what you can see is those two guys will cancel out. These two will cancel. These two will cancel. And then the series is going to keep repeating. So these things are always going to cancel. So this is going to converge to be 1. So this converges by the telescoping series to be 1. Now, it's not always going to be 1. So I want to give you an example that you have to make sure you see what cancels out. Okay? So I made up another example here. So 1 over n plus 1, and then minus 1 over n plus 3. So something like this. All right? So when I start with this, I'm going to say, hey, I have two different things being subtracted. That lets me know, hey, it's going to be the telescoping series. So now I just start plugging in. So I would get 1/2. When I plug this in, I get 1/4. So that's what I get when I plug 1 in. Now when I plug 2 in, I get 1/3 minus 1/5. Now when I plug in 3, I get 1/4 minus 1/6. Now when I plug in 4, I get 1/5 minus 1/7. And you can see now that these two are always apart. There's no 1/2 to cancel out. Is this going to cancel out? Yeah, that's going to cancel out with that 1/4. Does anything cancel that 1/3? And the answer is no, because these are all going to keep getting bigger and bigger. But now you can see that everything is going to start canceling out. The next one will actually be a 1/6 that'll cancel out with this guy, and it'll be minus 1/8. Okay, so if you keep going from here on out, everything's going to cancel out. It's called telescoping series. So in this case, the sum is just going to be 1/2 plus 1/3, whatever the things that didn't cancel out are. So if this is 3/6 and this is 2/6, this series is going to converge to 5/6 by the telescoping series. Okay, last one I want to give you guys of this is to kind of remind you how to do this. Okay, if I gave you a problem that looked like this, 2/4n squared minus 1. If I gave you 2/4n squared minus 1, this one looks super hard, but if you ever look at the bottom and you ask yourself, hey, can I factor that? Okay, this is where I said to you, if you can take 2/4n squared minus 1, if we can make this be a over, and let's just 2n minus 1 plus b over 2n plus 1, if I can make it look like this, it's hopefully going to be a telescoping series. Once again, I'll need this to be a minus, but when you do this, just like I taught you, you multiply, you set 2 equal to a times 2n plus 1 plus b times 2n minus 1, because really two fractions are equal, we set their numerators together, and then you strategically pick 1/2. When you pick 1/2, this becomes 2a, so a is 1. So this guy is really 1/2n minus 1. Well, when I pick -1/2, okay, that cancels out. This becomes -1. So that's how I end up with this as my telescoping series. Now, once it's set up like this, I do the same thing. I plug in 1, and I get 1/1, which is 1. When I plug in here, I get 1/3. Plus, now when I plug 2 in, I get 1/3 minus, when I plug 2 in here, I get 1/5. When I plug 3 in, I get 1/5 and blah, blah, blah. And in this case, they all cancel out and you get 1. So this will converge to 1. Okay, that's all the tests from the integral up. What we'll do tomorrow is we'll talk about all these, and they'll go quicker whenever you watch the video. But the last thing I want to do is I want to look at this page, which is 601. So I hope you guys can kind of see it. I hope. Anyway, the idea is these are going to be the problems. And I'm going to say to you, tell me if it just diverges or converges. That's the only directions. So if you look at A, the first thing I see is, hey, it's n over 3n. The limit of this thing is going to end up being 1/3. I can use the kth term test. If the limit is not 0, this thing is not going to converge, because this is eventually going to get closer and closer to 1/3. So you're adding 1/3 up. Well, if you keep adding 1/3 an infinite number of times, you're just keep getting bigger and bigger. So A diverges by the kth term test. So if you look at B, it says, hey, what's the summation as n goes from 1 to infinity of pi over 6 to the n? If you ever have anything to the n power, think geometric series. Well, there is no way out in front, but we can assume it to be 1. So now I just look to my r. If my r is less than 1, what does that tell me? Well, if you read here, it just tells you, though, because the common ratio of terms is less than 1, r is pi over 6, we know it converges. We could actually find that sum if we wanted to. And the last one I wanted to look at is C here, because if you look at C, n e to the negative n squared, if you look at that, you're going to say to yourself, you know, I can integrate that because the derivative of my exponent is out front here. I can integrate that, so you can try to use the integral test. And you'll see that in this case, it will converge because the limit will actually be a specific number. Okay, well, that's 8.1 through 8.3. The homework problems that I would like you to attempt is going to be right here. And I think what I'm going to do is try to actually videotape me just going over the problems so you can watch this after you do it and kind of grade it yourself. 8.1 is just the sequences and series I'm not worried about. So we start testing here, and I would like you to do 7 through 19. In 7 through 16, it just says, tell me why it diverges. So it's going to be the kth term test, the geometric series, whatever. You just need to tell me the test. So get used to seeing that quickly, and that'll help you out. Then the next three are, I don't even know which ones. But then I want you to do 33 and 34, and then 51 through 61. So that's 8.2's homework. And then 8.3 is 1 through 3, 11 through 19, and 53 through 60. That's exactly what your test will look like, except we'll add the other tests in there. One of Sydney Worth's comments gives you the book. So if you happen not to bring it home, you can look in the book, and those are your problems. Good luck, and contact me if you need anything. Thank you.